Hello everyone, welcome back to ExamPrepTool. So how are you guys? I hope you are doing well. So today we are going to talk about yet another lecture, yet another set of problems. I hope you're doing well. I hope you're enjoying these sessions. I hope you have covered whatever we did in the last session. Okay. Uh, just for a moment, let me just check whether audio and video is fine. Just wait. Okay. And then please keep sharing, keep liking if you're enjoying it. Okay. So yeah, I guess it's good. So we already have this thing in our mind that what we are going to discuss. So today we'll be solving problems on KNN, K nearest neighbor, decision trees, and naive Bayes. So these three are going to be something which we'll be discussing today. And I hope you have revised. So we have a proper presentation which we'll be sharing very soon. So, but before that, I hope you have revised, and we are going to get started very soon. Okay. 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 So, as you know, like, let me just share my screen and then we'll get started. Okay. Let me open it up. Mm, yes. Now we'll be getting started. Just let me know. Yeah, I'm here. It's fine. Let me share the screen. We have RIC. Yeah. So let me know if my screen is visible. It's not coming. Yeah, I guess this one is fine. Okay. Let me just take a little bigger one. Yeah. Now I guess it's fine. Cool. So now we'll be getting started. So as I talked about that, okay, today we'll be talking about yet another session, set of problems on KNN, K nearest neighbor, naive Bayes, and decision trees. And then, as you know, like we have already planned that what we are going to do is we'll be having a cheat sheet. Then we'll be solving some set of problems, and after that we'll be having a guidance session. Okay. So let's get started. Uh, so if I talk about the cheat sheet, you can just go through this. I can share these cheat sheet with you as well. So I hope you're aware of this thing. Just a simple idea that how does your KNN work. So we are having it over here. That what do we have in KNN nearest neighbor? What is the idea? What are the distance metrics we use? The formula we use? What are the pros and cons? In brief, this is what we are having. Okay. Now, if I talk about what is the next algorithm we are having is, I hope like a very simple thing we are having over here is the K nearest neighbor would be basically looking at what are the nearest neighbors I'm having, and based on that, whichever would be having the majority, I would like to classify my data point as belonging to that particular class. If it's a regression problem, in that case, I would like to take the average of those neighbors. Okay. So distance we talked about, formula we are clear. So it's just telling me the argmax. That means for whichever class we'll be having maximum number of neighbors, we'll be going by that. Pros, it's non-parametric, effective for small data sets, and computational expensive for large data sets, sensitive to irrelevant features and noise. Okay. Now what's next we are having is naive Bayes. So for the naive Bayes, it's like a simple kind of a Bayes classifier. But what we do is we have a very strong assumption over here, because of which we actually deal with it very beautifully. What are the type of naive Bayes we are having is Gaussian, multinomial, and Bernoulli. It's very fast. We require very little training data. We don't really need high data. It actually works with the high dimensional data as well. The only problem we are having, like the major problem, not the only problem, is, as you know, we talked about this, that there is a assumption that features are independent, conditioned on class labels, okay, which need not be true in our day-to-day life. The next we have is decision trees. So what we do is we have an entire data set, which would be like we have a number of data points within a particular node, and then we keep splitting that data point from that node based on some criteria. What are those criteria? That is like information gain, entropy, or gain impurity. So we generally try to minimize the gain impurity or entropy, or basically maximize my information gain. Interpretable, like we have simply if else kind of a thing. If I have this particular category, I'll go left, if not on the right. And similarly, if we have continuous variable, we have something for that, because I have a question related to that, so I would not really be discussing right now. We'll be discussing that very soon. Now there are important formula and interpretation for all these three information. Basically the splitting criteria we are having: gain impurity, entropy, and information gain. Okay, so I have a slide for that, which would be very useful for you to understand, I hope. And then we have information gain, which actually talks about what was the entropy initially for my node, and then if I'm splitting, what is the entropy in that case I'm getting if we just subtract. So weighted entropy, if I just subtract that, in that case I'll be getting the information gain. Okay. The gain impurity, on a similar side, it actually tells me that what is the kind of impurities I'm having. So if like you can see, like we have a very simple formula: 1 minus summation of all the p's what we are going to have. Okay, so in any case, if we have p equals 0 or 1, in that case we have the best possible case in which my impurity would be 0. But if we are not having, if we are having any kind of probability values which are non-zero, in that case we'll be having more impurities. I hope we are clear. So next we are going to talk about now problems. Okay, so now I guess you're ready to get started with the problem solving. So let's get started anyway. So here are your question. I'll give you some time to solve that, and in the meantime think about this, because I don't want, because this is a live class, so take the advantage, take your time. I'll just answer each and every question after 1 or 2 minutes. Okay, so I'll be taking at least 1 minute. I'll be giving 1 minute to you guys so that you can actually solve it. So this is the first question we are having on KNN. Try out. So I guess we had enough of time. I hope you're trying. So let me just help you out over here. I guess I had a space over here. Yeah. So we have a space. Let's just talk about how can we solve it. So like, see, remember this, that whatever we have over here, these are very simple questions. Always, basically, you need to just understand how does coordinate geometry work, and then you will be able to solve most of the time every question. Okay, every question most of the time, if you understand coordinate geometry well. Okay, so just going by the idea. So if I just take that up, okay. So let me just consider something like this only over here only, or I can just take the next slide. That would be better, but I need to just go back one again and again. Let's see. So what are the data points we are having is, I guess we are having x2 in between -1 to 3 and -1 to 2 as this one. So let me just write -1, -2. Here we have 0, we have 1, we have 2, we have 3. And over here also we have 1, we have 2, we have 3, and over here also -1, -2, something like this. So what are the class labels we are having? So consider this is my x1 and consider this is my x2. If I'm having this, -1, -1 is a negative class. So let me just take another color for this. So yeah, this would be better. -1, -1 would be your negative class. -1, -1, -1, -1, -1, this would be a negative class. Oh, this color is not visible, I guess. So let me take up something like this. Yeah. So this is my negative class. Right now, let's just take it like this. -1, -1. What is the other one? Negative class 0, 2. 0, 2 is this one. Then we have is 1, -1. 1, -1. Something over here. What do we have next? 1, -1 is done. 2, 2. 2, 2. So this is something like this. So these are all the negative class points, the green ones. You can see clearly. Okay. Now, what are the rest of the points? That is going to be your positive points. So let me just mark 0, 1 is positive. 0, 1 is positive. Next is 1, 0 is positive. 1, 0 is positive. What's next? 1, 2 is positive. 1, 2 is positive. Okay. Then 2, 3 is positive. 2, 3 is positive. So let's just check out. We have 4 negative class, 4 positive class data points. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And what is the data point we are actually looking for? 1, 1. Okay. We need to identify this particular one. So let me just mark it with some different color, say black only. So this is my test point. And I need to find out using Euclidean distance what should be the class it shall belong to. So if you just look at this, it seems to be very simple. What is going to be the answer? And what we are talking about is 5 nearest neighbor. Okay. So let's just mark it up. What are the neighbors we are having over here? I hope you can see this. So these are the closest one right now, just at a distance of 1, 1, 1. So 1, 2, 3. What are the other set of neighbors we are having is this one, which would be at a distance of √2, because this distance is 1, this distance is 1. And if you just want to use Pythagoras theorem, or if you understand coordinate geometry, this is going to be very simple. √2 would be this one. Okay. So this is the 4th point, and then this is the 5th point, which is again at the √2 distance. So what is the majority class? The plus is the majority class. So in that case, A is going to be our answer. I hope it's clear. And I hope you're understanding. Okay. So this was our first question based on nearest neighbor. I hope you could understand. Let's move on to the next question. If it's fine, I'm waiting. If anybody in the live session have any doubt, please let me know. Then we'll proceed further. Okay, I assume there is no problem. Let's go to the next question. And this is really one of the most interesting question we are having. So I hope you understand what is the Manhattan distance, because that is being used over here. Another thing is it uses one nearest neighbor. That means I would just look at the nearest neighbor, whichever I'll get, that is going to be my class. Okay. I'm not going to talk about 2 neighbor, 3 neighbor, just one nearest neighbor. That's it. Cool. So let's just go through the problem and then understand what is it asking to do. And then we'll be solving this problem. The table below shows the test set for a one nearest neighbor classifier that uses Manhattan distance. That is, the distance between 2 points at coordinates P and Q is P minus Q modulus. So that means if I'm talking about at any point of time, if these are the 2 coordinates P and Q, in that case, I just need to find out P minus Q modulus, which will be giving me the distance between them. And please see, what we are having is just one dimension. So it doesn't really matter whether you're using Manhattan distance or Euclidean distance. That should be clear to you. Okay, we are not just solving the problem, we are understanding well how do we solve it. Okay, and what is the extra information which we can derive, which makes it intuitively easy for us to understand what we are doing is fine. Now, this is clear, Manhattan distance, the only attribute x. So as mentioned, we have only one attribute. That means we are actually playing on the one dimensional space is real valued, and the label y has two classes, 0 and 1. Okay, cool. Suppose a subset containing n less than equal to 8 example is selected. Now, if you just check it out, how many data points we are having over here? 1, 2, 3, 4, 5, 6, 7, and 8. In total, we have 8 examples over here. Now, what we are saying is, suppose a subset containing n less than equal to, I might take all these or something less than that, this from this set to train the classifier. So I'll be taking a subset of this data set I'm already having to train my classifier, which is one nearest neighbor. And the accuracy of that shall be 100%. Very important. Accuracy of that shall be 100% when tested on this set. So that means whatever subset I have taken, basically if I'm saying, let's suppose for an example, if I took 6 data point from this. So if I'm training on that, and if I test on that same 6, after training on these 6, if I'm just testing on all these, what should be my accuracy in that case? I shall be getting 100% when I'm testing it on all the 8 data points over here. Now, what we are talking about is what shall be the smallest possible value for n. That means we need to just think about and solve for what should be the n value. That means what should be the minimum number of data points I shall pick from this data set, such that once trained, if I check out my accuracy on entire set, whatever we are having, this 8 data points, I shall be getting 100% accuracy in that case. Okay, so how do we solve this question? This is very interesting. So for that, what we can do is right now, to just go by that, let's just draw a line and understand what is it saying. So if I draw, so what I'm having is, so -5 to 8 we are having. So let me just start from -5 only. -5, -4, I'll be having -3, -2, -1. It doesn't matter whether that is present or not. Just for the same space thing, I'm just writing all the data points. 1, 2, 3, 4, 5, 6, 7, and 8. That's what we have. Like -5 to 8, you can see. So these are all the data points we are having. So if I just mark it up, what are being used over here is, we have -5, we have -4, we have -1, then we have 0, we have 1, we have 3, we have 4, and we have 8. Now, if I just talk about the class, I can write it now. So -5 data point was having 0 class. So let me just say negative class over here. -4 had positive +1. Basically, it's 1. So I'll just write it as plus. Again, for -1, it's negative. All have negative, 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 negative. Over here we have is positive. Okay. Now I hope until this point we are clear that how is my data set relying on this one-dimensional line. These are the violet dotted points are actually the data set points we are having. Now what we need to do is, I need to pick up some subset from this. What shall I pick up such that if I use that to train, I hope you know what do I mean by train. So what would that mean for a one nearest neighbor classifier is, I would just use those data points as only data point and would test for rest of the data point I'm having. That means if I, let's suppose, picked up 6 data points, and in that case I'll be just using those 6 data points to basically test for all 8 data points, that what is the accuracy on all the 8 data points using these 6 data points only. Now we will check that, okay, what is going to be my accuracy for that. Now for 6 data point, the same data points which we'll be taking as a subset, that would be 100%, but the remaining two would be helping me in deciding that what is going to be the accuracy. If those two are also classified correctly, then I'll be having 100%. Similarly, if I say if I picked up 5 data points, then in that case those 5 will be having a definitely a good kind of, what should I say, uh, um, those 5 data points tend to have like 100% accuracy, but the rest of the 3 are going to be playing major role in determining that, oh, what is going to be my accuracy, overall accuracy. Okay, so how to do that? Now you just need to think, what is the division I'm having of overall all the classes? So I hope you can see it's something like this. If I just would like to show you, can you see? It's something like this. That means if I just talk about this one, we have negative class over here. This entirely is a negative class, and this overall have positive class. Okay, I hope you're clear on this. Now that means we already have a majority of negative class data points. Now I need to be very careful. See, if I pick up any data point over here, like out of these 5, they tend to give me the best accuracy for all these neighboring ones. Okay, why so? See, if I just include 3 over here, just look at the distance of -1 to 3. What is that? 4. And what is the distance of this? 2 minus 4. So over here I'll be having one problem, that we have the same distance of this point -1 from -4 and to 3. So it is something like a problematic situation if I am not including -1. So -1 is a midline over here which I shall be picking up for my subset to train. Why so? Again, going by that, if you just look at this particular data point, what is the distance of this data point on the left hand side? The closest data point which we are having is -4. And what is the distance? Overall distance would be 3. Now if I just go over here in this particular direction, I am having this one is fine, this one is fine, this one is fine. Like the farthest one is this one. Sorry, this is at 5. What is this? Yeah. So overall, if I just talk about this, yeah, on the right hand side we are fine, but on the left hand side we have to be careful. So we need to just think about those data points, especially which are on the boundary line for me, on the boundary line. Okay, so that means -1 is important for me. Why this -4 is important for me? Because if I don't pick it up, in that case every data point over here would be classified, would be from negative class, because I had just one example which was positive on the left hand side, and if I'm not bringing that particular data point as a part of training, in that case everyone would be classified as negative. So we are going to be wrong over here. So that means this has to be taken seriously. That means this has to be selected. This has to be selected. What shall be the color? Okay, yeah, this has to be selected. Now what's next? On a similar line, if you just think about -5, if I just pick this up only, in that case -5 would be classified as positive class, because it would be just the nearest neighbor to this -4 data point which was belonging to positive class. So just to help me out in identifying this as negative itself, I have to include this as well. So you can see these 2 data points are already done. We have to bring them anyway. Now on the same side, if I do not bring this one up, this +8, I would never be able to classify a data point over here which is positive, because this was the only data point. It's like one-man army, which is basically handling the positive case. So that means this also has to be bringing. Now, are we done? Do we need just these 3 data points, or we have a problem over here? So if you just look at this, we have -4a here, +8 over here. Both were actually positive class. Now, to help these values, because there is no candidate right now which is belonging to the negative class, so I have to bring in a candidate from the negative class so that the neighboring ones can be classified as negative class. Now which one to pick? That is going to be very important. So if I just look at this one, let's suppose if I include -1, if I include -1. So what is the distance of -1? See, on the left hand side I'm clear, on the right hand side this is clear, this is clear, this seems to be clear. -1 to 3 is the distance overall is 4. What is the distance of this from this? It's 5. So we are having, you can see, like this is correctly classified as negative with one nearest neighbor. What about this? -5 to 4, the distance is going to be 5. I hope you can see that. What about the distance of 4 to this one? This is 8. So I hope you can realize this one is basically having a trouble over here. This can be classified as a positive class if I just pick this one over here. Okay, if I'm just picking -1 over here, is there anything which we are missing? This is the smallest x value. Okay. Oh, if we have a tie. Okay. What about picking 0 over here? Just look at this. If I pick 0 over here, what would be the classification for this one? It would be negative, it would be negative, it would be negative, it would be. So see, we will be having again a problem over here because it will be a tie over here. Because distance from 0 to 4 would be 4. Distance from 4 to 8, because this would also be there. We have selected this. So this would also be 4. In that case, we are having a tie. And for the tie, what do we say? Use the example with smallest x value. That means if I'm using 0, what is the smallest value? 0 or 8? It's 0. That means whatever is the class of 0, that would be classified. So that means it seems fine. So what is going to be the data point which shall be picked up over here? Taking -1, this was not really helping this one. If I take 0, in that case, I'm able to classify this properly. And these are already handled because these are just the very nearest neighbor only. So this has to be included, the 0 data point. So that means what are the overall number of data points we are talking about is 4. And what are those? -5, -4, 0, and 8. I hope you're getting this. Everyone. Yeah. So what is going to be the answer over here? The answer is going to be 4. N is going to be 4 for us. I hope it is clear. In case you are having any doubt, please let me know. Okay. Cool. So we'll be talking about the next question. You just think about this particular question. If you have any doubt, please let me know. I'm waiting for just a few seconds only. Okay. Just think about this. What we actually talked about this over here. Just a quick question for you to basically answer. Can you think of this? Is it the unique solution what we are having? Is this the unique solution? The moment I said -5 and -4 and 0 and 8, is it the unique solution? Can we have another solution which is better than this? We need 4 data points. That is clear. -5, -4 and 8 were already important. 0 is something which is helping me out over here. 0 was important. Instead of 0, can I select any other as well? So answer is yes. What can be that? Think about this. Can I include 3? Look at this. This was having at a distance of 4. We talked about this. This was having 3 distance. So 3 would be like if I just think about taking 3 among these, this would be a problematic because this can be classified as positive. 4, we can't really again take this. So this is cancelled. This is cancelled. This was having trouble. This is working fine. What about 1? These are just neighbors. Fine. What about this? 1 distance from 1 to 4 is 3. 4 to 8 was 4. So yeah, this is also working fine. So if I talk about number of solutions with minimum n is -5, -4, 0 and 8, and -5, -4, 1 and 8. Okay. We have 2 solutions. In both we have n equals 4 and both can be used. So we are not just solving the problem. We are getting into a proper analysis that what could be the possible subsets we could have such that we still could be getting 100% of the accuracy on the entire data set we are having. Okay. I hope we are clear. So let's move ahead to the next question what we are having. So now enough of the numerical based problems. Now we have something theoretical over here. KNN has curse of dimensionality. Yeah, we know that. Now, what is the problem with the high dimension? High dimension causes what? Does it lead to faster computation? Does it allow linear separability? Does it give me automatic feature selection, or distance becomes similar? Neighbors are meaningless. Very important point over here. See, the answer can be obvious for you right now, but we need to understand why. If we are into a very high dimensional space, just think about having like 200 dimension, 300, or you can just go beyond that as well. Now, within that, think of kind of sparse data, or even if it's not sparse, every data point would be lying in kind of every corner of the dimensional space we are having. So if we are having 100 dimension space, in that case, most of these data points would be lying very far from each other. Okay. Now that means if I am considering their distances from each other, that would be nearly same. That means if I want to find out the neighbor, it would be giving me similar kind of distances for each of the data point we are having. Because if my dimension is more, it's like talking about this. So I am having, let's suppose, 100 dimensions. So 1, 2, 3, 4, 5, 6, up to 100. So in that case, I'm saying not all the dimensions might be giving the contribution to the like a distance. But I know if I'm having sometime second and sixth dimension and maybe some 98th dimension, sometimes I might have fourth, seventh, or 90th dimension, something like this. What would be having is, what I'm talking about is, overall, if you just look at the high dimensional space, each of those points would be lying very far from each other because they are getting into further separation boundary because of these high dimension. Now, the moment you are getting into higher and higher dimension, all these points are going farther from each other, which are making them nearly at the same distance from each other. Why nearly at the same distance? Because if you have so many distance dimensions, think about this. The way you calculate the distance, you would be taking something like this only, like x1 minus. So let's suppose I'm talking about the first point. Oh yeah, let me just write it like this. x2 minus. So let's suppose x and y were two data points, and I'm calculating the distance between them. And these x1, x2, x3 are just dimension of that x data point. Now just think about this. The way we are calculating, all the contribution of these dimensions overall aggregated might be same most of the time. And that's actually, that would happen because we have so many dimensions. There would always be some addition happening, some minute, but it would always be happening, giving me on an average kind of a similar distance among every data point. So that means the neighbors in that case would be meaningless and distances become similar. I hope you got that what is the problem of cursive dimensionality with respect to the KNN over here. Yeah. So let's go to the next question. I hope you could understand. Okay. So for regression, while using KNN, neighbor values are 2.1, 3.4, and 2.8. Now, what is going to be the prediction? As I mentioned, what we are going to use? Are we going to talk about mean, a median, or a mode, or some weighted mean, which needs the distance? What actually happens in the regression with KNN? If anybody having any idea, do let me know. Anybody? So I hope you remember I talked about the initial part of this as well already, that it is going to be overall average. So what is going to be this? 2.1 plus 3.4 plus 2.8 divided by 3. So basically we look at the mean, and that is going to be my prediction. So A is going to be the correct answer for this one. Okay. I hope again you could understand. Easy question, understandable. Now we have something different. Unscaled features in KNN with different ranges cause what happens? So what I'm saying is, We have unscaled features. That means we have not done any kind of a feature scaling in KNN. And each of the feature have different altogether ranges, different scale. Now, what is the problem if we have different scale of features? We need to calculate distances. And the moment we talk about the distances, distance would be dominated by those features which have higher scale, okay, higher range. So that means it causes a problem that those like what should I say, those data points which have which have the higher value of the feature values which had high scale would always be very farther from each other, okay, or basically that would be dominating my distance part. So in that case, that creates a trouble with KNN, okay. So high range features dominate the distance. No effect, false. Automatic normalization doesn't happen. Reduce bias, nothing like that. So what is the correct option? A. I hope you're getting. Let's move to the next question now. What do we have? Again, an interesting question. So we have a 1D classification problem. A 1D classification problem has training points. We have like 4 data points, A, B, C, D. Their classes are written. So that means it's again on a like a number line. If I just would like to write. So we have 2, 5, 6, and 10. Something like this. What is the class of 2 and 5 and 6? So if I just write down with this, so let's suppose C1 is positive. Okay, so this is positive, this is positive, and I would say C2 is negative. So in that case, this is negative, this is negative. We are using Manhattan distance. Which class is assigned to the X new, where my new is actually 4th data point. So like I'm actually looking for what is going to be the class for this particular data point over here. What should be the class for this? We are using the Manhattan distance. And the k is equal to 3. That means we'll talk about 3 nearest neighbors. So the very closest nearest neighbor is this only, at a distance of 1. This at a distance of 2. This at a distance of 2. So you know we have one at a distance of 1 units and 2 neighbors at a distance of 2 units each. So what is going to be the class in that case? I hope you can see we have the negative class dominating over here. That means it is going to be C2 over here. Again, very simple. Just a simple, what should I say, application of Manhattan distance and what we know about the nearest neighbor. I hope you got it. You got this. Let's move on to the next problem. Again, it was very easy. A final one with some variation over here. I don't know whether you have heard about the weighted score for k nearest neighbors. What is that? I'll talk about this over here. So in a 2D feature space, a new instance X new, that means a new data point, it's a test data point, which is having coordinate 5, 1 needs to be classified. The distances to its 3 closest neighbors are, so distances are already given. That is 1, 1.5, 2.0. Their respective class labels are class A, class B, class C. Sorry, class A. So that means if I'm saying the distance to those data points already belonging to class A are 1 and 2. Okay. And distance to a data point belonging to class B is 1.5. If you use distance weighted KNN, what is that? I'll talk about that very shortly. And we are using a k equals 3. So, and we have the 3 distances only. We need to just use them. Like we can directly see that this is the one which is dominating. So I must be assigning this only. But we use the weighted score for each of the class. It's not the majority of the class by which we actually go for assigning a class label. We actually calculated a weighted score for distance weighted KNN. Now, how do we calculate that weighted score? So score is actually given by whatever. So if I'm saying score for class A, so whatever were the distances from the data points belonging to class A, we'll just use those. Now, what does it do? Like, how does it actually help? It's a simple idea over here that if I'm having those data points which are farther, in that case, those should not really be considered as the the deciding factor. It's something like this. So let me just mark it up, which will help you understand. Do we have a, yeah, we do have a space. Let me just give you an example. Just think about this. This is a particular example I'm bringing to you. And let's suppose this is the data point I'm having. And we are talking about the two-dimensional space. I have a data point over here which is belonging to negative class, negative class. Then we are having something over here belonging to positive class, positive class, positive class. If I just look at 5 nearest neighbor, in that case, you can see plus class dominates. So I shall be assigning this to positive class. But just look at this. The negative class is most closer to this one. Can you see? And we have these three, but they are very farther from this. So apart from how many data points we are having, we shall consider the idea of distances as well. So we have to consider the addition of number of data points we are having, but in the inverse relation of their distances. If distance is more, in that case, contribute less for deciding that it should belong to that particular class. So how do we do that? 1 by d for each of the class. So like if I'm actually looking for what is the score for, if what is the score for assigning it to a class, I'll be calculating this distance. So 1 by d1, d2, d3. Okay, if these are 1, 2 and 3. And for negative class, what I'll be doing is, let's suppose this was 4th and 5th data point, I'll be doing this. Now I'll look at these values. Whichever would be greater, that means that is going to be the class which we shall be assigning to this particular data point. Okay, I hope the idea is clear. So there was a reason of bringing it. If that point is clear, we just need to do the simple calculation to understand what should be the answer over here, final answer over here. Now what is going to be that? So we know already A is the majority class, B is the other one. Now we just needed the weighted score for class A. So what is going to be that? 1 by 1 plus 1 by 2. The distance was 1, distance was 2. That is 1 plus 0.5, giving me 1.5, and this is the answer. I hope you could understand this. Okay, interesting questions. KNN. So now we'll be changing the gears. We'll be talking about the next algorithm we are having, next model we are having in the line, which is going to be our nearest neighbor, naive Bayes. Now we'll be having some set of problems from naive Bayes. Now it's very simple. You remember what was naive Bayes? We have a cheat sheet already. When using naive Bayes classifier for prediction, what rule is used to assign a class to a new observation? Can you recall? Can you think of it? What is the rule we use for the naive Bayes? It's simple, very simple. Think about this. So I hope you remember, in naive Bayes, we are actually calculating the posterior probability, something like this. Probability of y given x is being calculated based on x given y into probability of y upon, we have some marginal probability in the denominator, which is basically used for the normalization. We could avoid it if we just want to know, if we just want to compare this score, because the denominator would remain same for every class if I'm using. So if I'm using something like this, instead of y, I'll be having just y2, but the denominator would still be same. Okay. So in that case, we just compare the numerators. So I hope you recall this. So this part is actually likelihood. This is called prior. The denominator is called evidence. And this is my posterior, which we try to maximize. Posterior. Hence, the answer is going to be maximum a posteriori rule. MAP. I hope it's clear. Easy. Again, very interesting. Question number 9. Think about this. What exactly is going to happen? Very important question again. Let me tell you. It's again interesting. What shall be the answer over here? Think about this. What is the answer? Could you think about this? See, the first option is very short, very easy. Each feature is independent of all the features given the classes. Remember, we do not just say independence of the features, independence of feature given their classes. That is very important. Okay. So A is definitely correct. Now, what about the other options? All features are equally important in predicting the class labels. Yes, they like, I hope you know the equation. So we had something like this where we actually talk about each of the features being used for the classification purpose. Okay, we use something like this. I hope you remember. So you could see that in the beginning as well. Okay, so we will be using each of the feature. Each of the feature is important. What about the C option? There can be missing values. Yes, there can be missing values, but is it our assumption of the base classifier, naive Bayes classifier? Answer is no. That is not the assumption. Class labels are mutually exclusive. Yes, the same data point cannot belong to two different classes. It has to belong to one class only. Okay. So yeah, that is also true. I hope you could get this. Cool. Let's talk about the next one. To prevent computational underflow when calculating the likelihood term. So I hope you know, like we get something like this, where we will be having product of all these likelihood probabilities. Okay. Now, in that case, how do we actually solve? So I hope you remember. So lastly, we are just talking about there is a summation happening. So if you can recall what happens is naive Bayes is, I hope you can recall, there's something happening. So because the product is a very complex thing, if we have a number of features out there, so just think about 100 features. So in that case, it would be product of 100 features. And if I'm just talking about the probability, product of all that would be very small. So just think about product of all the values between 0 to 1. If it's 0.9, 0.8, even if I consider 0.9, just think about 0.9 to the power 100. What would it be? Very less. So that is a problematic thing. We don't really want to decrease the value of probability, but we still want to capture the same effect. So what do? So we do log both the sides for the posterior, and on the right hand side, we have the log of likelihood into your class. Now, if I'm just talking about that, what would be happening in that case is taking the log over the multiplication terms actually converting to the summation. Okay, so it would be something like this. Post it. Log of p of xj given ck. Okay, and we'll be actually going on this I. Sorry, I. It was I. So in that case, the implementation often calculate the score by summing which transformed value logarithm of probabilities. I hope again you could understand. Very relevant thing over here. Cool. Let's go next. What we are having is, suppose you have a 3-class problem. There are 3 classes where each class label y belongs to 0, 1 or 2. So that means I'm going to have 3 classes. Let's suppose, okay, so we are calling it 0 or 1 or 2. Okay, we are having only these three classes. And each training example X has three binary attributes. So that means I'm having three features also, X1, X2, X3. And each of these would be having a binary value. That means either it would be 0 or 1, either 0 or 1, either 0 or 1. Then in that case, how many parameters do you need to know to classify an example using this name-based classifier? What is the number of parameters required over here? Very important question, very interesting, very simple. So what do we need for classification? If you just look at the formula, I just talked about that. You need actually something like this. Into P of yk. I hope you remember this. Okay, in the numerator we have this, in the denominator doesn't matter because I can just always compare the product of likelihood and prior to find out which class shall my test point belong to. Now that means I would be needing this and I would be needing this for overall calculation. Now the moment I am saying what is this, this is going to tell me, given the class, what is the probability of having that particular value of X. Now what is the possible values for any X given a class, either 0 or 1. Okay, so that means like if I want to write it in simple format, I can write it like this. Either it would be 1 if I'm saying that y is equal to 0. Let's suppose just one class I'm talking about, or I'll be having this one. X1 would be 0. These are the only possibilities I'm having when talking about the same class. So when y is actually the class is a 0th class, in that case y1 can have 1 or 0. And I hope you know, if I know this, I can calculate this very easily by doing 1 minus this one would give me this particular probability. So that means for just X1 only, given a particular class, I just need one parameter. Now, how many such features we have? For each of the feature, we have binary value. So one I needed for this one I would be needing for X2, one I would be needing for X3. So overall, I need three features for a particular class. Now, another important thing, how many class do I have? Because I'll be needing these parameter for each class. How many class do we have? 3 multiplied by 3. This was only helping me to find out the parameter which will be telling me what is the probability of X1 being 1 or 0, or X2 being 1 or 0, or X3 being 1 or 0 given a particular class. This is going to tell me overall 9 parameters. Now what's next? Again, very important. We got this 9. Another thing over here is going to be, once I know this is 9, how many parameters would be coming from, like, is it done or do we need some more parameters? So if you just look at this, very important, I need this as well. Now what are the different possible values of yk? Y can be 0 or 1 or 2. If I know any two, I can find out the other. Let's say this is having p probability, this is having q. Can I calculate this one? Probability of y being 2? Yes, by doing 1 minus p plus q. So that means for yk, that means probability of y belonging to a particular class, how many parameters do I need? I need 2 probability values. 2 probability values, okay? So 9 plus 2, 11. That is going to be my answer. I hope you could understand. 11 is the answer over here. Very simple. Okay. Very interesting, very important problem. Now this we are having again an important problem because you need to understand how does smoothing works. Okay. We have a data set over here. You need to tell me all of these probabilities value with and without smoothing, So remember, the smoothing is only done for the case of conditional probability given the class condition, like which class we are talking about. In that case, we apply the smoothing. If it's the simple probability of a variable I'm looking at, we do not really be using the smoothing in that case. So what would be happening over here for this particular case? So that means, let me just calculate this over here for you. Without, sorry, first we'll do without and then we will do with smoothing. Okay, and let's just write out all the possible calculations, what is going to return me. Okay, so what is the probability of playing? So we have like 4 rows, and if I'm saying play, that means I'm talking about the play would be happening. So that means in that case, or we will be playing, so in that case, what is the probability of that? 3 out of 4. With and without, it's same. Okay, probability of not playing, again very simple, 1 by 4, 1 by 4, because that doesn't really help me in anything over here. The smoothing will only be coming for the conditional probability. Okay, now once we have it, what would be happening for probability of sky being sunny given play? And the moment we are saying play, it means we are saying play equals to yes by default, because for the play equals no, we have another case where we are saying negation of play. So for this one, what I need to check is I need to consider only these rows. Only these rows. Okay. So given this is happening, what is the idea for sky being sunny? So you can see whenever it was like yes, every time the sky was sunny. So this is going to be like, can I remove it? Yeah, I can remove this. Let me just write down this a little higher so that we do not really consume much of space. So this was 3 by 4, 3 by 4, 1 by 4, 1 by 4. If I'm talking about this, then I'll be talking about this, then we'll be talking about this, then this. Okay. So now if I'm talking about this and without smoothing I'm talking about, that means what I'm saying is I'm going to have we had only how many rows we had? We had 3 rows. Out of that, how many had sky equals sunny? All. So that means it is 1. I hope it's clear. Now on a similar side, if the sky is, so I am actually looking for sky being sunny when not play. So that means in that case, I'll be looking at this particular row. Okay. So that means if the sky is not, if we are not playing, that means I'm looking at this one. What is the probability of sky being sunny? It's 0. 0 by 1. It's 0. Okay. This one. Let me just remove this. So this was 1 by 1. 3 by 3 giving me 1. This was 0 by 1 giving me 0. Okay. I hope you could get this. Now, on a similar line, if I talk about humidity, this particular column, if play is happening, so we have these two and then these and then this separately. Okay. When not play, in that case, I need to consider this. So if play is happening, in that case, humid is high. So how many of those cases? 1, 2. 2 out of overall 3 rows. So 2 out of 3. And what about this one? Humid being high, when no play is happening, no play, humid being high, it's 1 by 1. Okay, I hope we are clear. How did we calculate these probabilities? Okay, for the naive Bayes. Now, talking about with Laplace smoothing, what would be happening in that case? For probability of sky being sunny, given play is happening, so, or we are going to play, what is going to be that? So for the smoothing, what would be happening? So we know like what we are going to talk about is we are talking about overall rows and how many times we had that value. Okay, value k. Now when we talk about smoothing, in that case we add +1 in the numerator and total possible values of k we had. That means for that particular column, what were the different values we had already, because that would help me in bringing no zero probability, because if I have one of the zero probability, what happens is in naive Bayes we are multiplying the probabilities. I hope you remember. And in case of logarithm we are adding, it's fine. But if I do not take log, we are multiplying. And because of any feature, if any feature had a zero probability, the entire probability or the posterior value will become zero. That we don't want. So just to adjust for that, to help out there, we do Laplace smoothing. And this is what we do. So what is going to happen over here? Here, here, and here. So probability of play, that means we had a 3 rows. So again, in the numerator, we had 3 plus, what was in the numerator? We had 3, but we will be adding plus 1 over here. And what are the different values of sky over here? It's 2 different values are possible. So what we are going to have is 3 plus 1. It's 4 by 5 I'm going to have. I hope I'm clear. Similarly, if sky being sunny, provided not play happening, we had just one row. So 1 in the denominator plus how many possible values of this one? Sky we are having is 2. We just talked about that. And what is the value over here? Is it sunny? No. So that means 0 plus 1 over here. We will be getting 1 by 3. I hope you're getting. So 4 by 5 for this one, 1 by 3 for this one. What about this one? Humid equals high for both the cases. So we already have the values. So denominator, we know we need to add something. In numerator, we need to add something. And for this one also, 1 upon 1 plus something plus something. What would be happening? So what are the different values of humidity we are having? 2 only. So 1 and 2, 1 and 2. What is it going to be? 3 by 5. What is this going to be? 2 by 3. I hope you could understand how we are calculating. It is very important. Something like this can definitely be asked. Very important. One of the important questions we are having. I hope we are clear. Very important question we had. Okay, now again on the decision tree. Okay, we had naive Bayes. Now we are done with the naive Bayes. Now what we are going to have is decision tree based problems. Very important. You can take a sip of water if you are like tired, but we are not. Okay, I'm not. So you can just take a short break before going for the next set of problems. We can have just 1 minute break or something like that. And make sure you're understanding everything, revise everything, flip your pages, look at all those things, what exactly we have discussed. Are you getting everything or not? Okay. Cool, guys. So yeah, let's get started. So again, we are having this based on feature one. Based on feature one, we are going to split and we need to find out the information gain. And we need to find out which will be having maximum best, which will be giving me best split. The moment I say best split, basically corresponding to each of these values, I must be getting maximum information gain. So I'll just tell you what to do. And in that case, you just calculate those values. We'll not be solving it entirely because we just have a formula over here, which we need to use directly. And then we are done. Okay. So let me just help you out with the formula. So how do we calculate the information gain? I hope you remember in the cheat sheet also we have already. Before splitting, what is the entropy? Minus after splitting, what is the weighted average of your entropy? What is that weighted average? Okay. And after calculating that, you'll be getting to know information gain for each of the split. Now for you to decide it properly, what you have to do is, based on feature one, let's just divide it. So let me just write it in the sorted order. So we have 11.7, we have 12.8, 15.3, 13.9 over here, 17.2, 16.8. So let me write it over here, 16.8, sorry, 8. Then we have 17.5, 23.6, 16.9. So we have one more data point. So let me say this was for this. Another data point for this, 16.9. And then 19.1. And if I try drawing a number line kind of a scenario, this is what we are having, this. We have this data point, we have 16.9 here, we have a 17.2 here, we have 17.5 here, 19.1, 23.6. Okay, so let me just write 16.8 over here, 16.9 over here, and 17.2 we are already having. So let me just erase this part so that we do not get confused. Okay, so overall we are having these data points. So if I'm talking about 14.6, 16.05, okay, please, before even that, let's look at the class labels as well. So we have A, let me just write down, A for 11.7, A, 12.8 is A, 15.3 is A, 13.9 is A, 17.2 is A, 16.8 is B, 17.5 is B, all are B, no, all are B. This is also B, this is also B, this is also B. Okay, so we have this is what we are having over here, and now we can see that what is the splitting we are talking about, and we are doing it on feature 1. So that's why I have written it on feature 1 only. So let me just mark those with this one. What are the candidates we are having? 14.6 would be somewhat over here, 16.05 would be somewhat over here, 16.85 would be something over here, and 17.35 would be something over here. So can you see like what is going to be the best split without even doing the calculation? Let's just look at this and understand and analyze. Can we really solve it without getting into the detail of the formula, without writing it, having to write it? Because if intuitions are clear, you are always good to go. So if I just talk about this, definitely this is not going to be a best possible thing. Why so? On right hand side, we have a B, pure class, again good. But on the left hand side, I'm having two Bs. I hope you can see this. Okay. Seems like a troublesome kind of a problem. Okay. What about this one? 14 point, whatever was this? 14.6. Again, on the left hand side, I'm having a pure node, but on the right hand side, I'm having two A's, which doesn't seem like something good again, because I know there is something bad happening within this part, because I have A over here, I have two B's over here. If there is something which can be done, that would be great over here in between these two. Thinking about this one, what we have is 16.05 and 16.85. 16.05 is going to be this one. Just look at this. We have a pure over here. We have only one, which is incorrect classification. Now, what about this one? If I just look at this, I have one incorrect over here, which is this one. I have one incorrect over here, which is this one. Now, what do you think, without even calculating, which one is going to be the best possible answer over here? Think about this. Take your time. It's very important. And you need to think about the weights as well, because how many numbers we have over here is 1 2 3 4. So if I'm talking about this one, I have 4 over here, 1 2 3 4 5 6 over here. Okay. And if I talk about this one, in that case, what we are having is we are having 5 over here, 5 over here. What do you think? Think about this, give some time, or you can directly use the calculation also to find it out. Okay. What do you think? You know the answer. If not, it's okay. You can just use the formula. So what I'm just telling you is we simply basically could eliminate these options very easily by intuition only, because see, you need to think about the number of data points as well and the number of pure nodes also. Okay, so you can see 14.6 and 17.35 were not giving me good because it was imbalanced with respect to the number of nodes, also with respect to the they were not pure nodes as well. But if I consider these two, it seems to be fine. With the 85, it seems 5 and 5 on both sides, but I'm having misclassification, one misclassification on each side. With 16.05, I'm having 4 on 1, 6 on 1, but one side I'm having pure, other side I'm having what? Oh. Other side I'm having is like a simple thing over here. So what shall be done? You can just calculate your information gain for each of these two, and you can just get the answer. So if I talk about what was the entropy initially, what is going to be the initial entropy? If you just really want to find out what is going to be your initial entropy. Initial entropy. So we have around, I guess 5 and 5 only. No, we have equal. So entropy initially is maximum over here. What I'm going to have is, I hope you know that what I'll be getting as well. So what we're having is minus point. Sorry, my bad. 0.5 log 0.5 plus 0.5 log 0.5. Okay, because I'm having 5 data points belonging to A, 5 data points belonging to B. What I'm going to get is log 0.5, which is going to get me log 1 by 2. Yeah, it's going to be 1 only. So this entropy is already 1. I just need to think about this one being minimal. Wherever this would be minimal, I'll be getting what exactly is going to be my answer. Now, I hope you know how to calculate the entropy. We have the formula. We just need to check out that number of data points within that particular node, how many data points we are having belonging to a particular class. And then overall, for the weighted average, I need to multiply overall what was the division as well. So that means if I'm just talking about this, what is going to be for 16.05 only, if I just talk about, what I'll be doing is, so let me just write down 4 upon 10 minus 4 by 4 log 2 of 4 by 4, and then again negative sign, 0 by 4 log, like I know like it's going to be 0, so like we shall not be really picking it up. And then on the other side, what we'll be having is, we have 6 data points on the other side, 6 by 10 minus 1 by 6 log 1 by 6 minus log 5 by 6, sorry, 5 by 6 into log 5 by 6, and then you will be able to get the answer. And wherever you'll be getting the minimum value for this, that is going to give you the best possible answer. Okay, because minimum is this, subtraction would be like you are subtracting lesser value, and overall information gain would be maximum. So this is going to give you the best answer. Okay, you can simply use the calculation and you'll be getting it. So that was all for this question number 13. Let's talk about the next one. Okay, we understood the entropy, we understood the information gain. What about for the same data set, that means this one only, Gini index? Do you know how to calculate the Gini index? Think about this, but right now we are talking about for feature 2, how we are going to do it. Very important. Think about this. What is going to be the formula for the Gini index? I hope you know that. Again, simple one. What we actually do to calculate the Gini index, it shall be clear. Let me just write it up as well for the feature 2 as well in the order, and then we can see this. We don't really have a space for this, but you can use the same kind of an idea. So you can just sort it up and then calculate your Gini index. Wait, need to rub it off. And even if you don't want Gini index, see, be it your Gini index, Gini impurity, information gain, entropy, everything would be giving you the same best split. The values for them would be different. It would be just values for them would be different going by the feature. Okay. So considering this feature 183.2, let me just write down. 183.2, 187.6. Oh, I have a number of small values, so let me not write over here. Let me write a little later. What is the minimum value? 151. 151.1. So let me just write it as 150 only for the ease of understanding. 150. Then what do we have next is 162. For ease of understanding, I'm not writing the decimal points. After that, within 170s, what we have is 171, 173, 179, 175, 177. So I guess all the odd values. 1, 3, 5, 7, 9. All the odd values. 171, 173, 175, 179. We didn't have 177. Yeah, we had 177. We had 177. 3 and 5 was also there. 177. 179. And after 179, what do we have is anything in 80s. 183, 187, 198. 183, 87, 98. 183, 187, 198. Yeah, we are fine. So let's see what are the values we are having for each of these. So 83, 87 is A. Let me just choose a different color. 83, 87 is A. 83, 87 is A. 77, 98 is A. 77, 98 is A. 77, 98. 75 is A. Rest are B. So again, a similar kind of a question over here. You are already knowing it. We had all the A's over here. We had all the B's over here. Okay. This is the problem. Like this is a kind of a boundary point we are having over here. Now, if I just look at this partition or this partition, I hope you can see. So what is the what are the values we are considering over here? Oh, so that is missing. Let me just write down what were the values which were actually talked about. Sorry, it's an incomplete question over here. I'll share this one. So A is 172.6 we are going to have. Then we have 176 wala point. Then we have 178 wala point. And then we have 185 wala point. You can just find out 176.35, 178.45, and we have as 188.4. Yeah, these are the options. So like 3 options around 170s, 1 option around 185. Doesn't seem to have a good answer. And yeah, so over here it seems to be something good. Let's see what exactly are these points talking about. 172, 68. Oh, even numbers. Good. So what are the numbers I'm having is, let me write 171 over here, 176. That means over here, and 178 over here. So what is going to give you the best split? What do you think? Again, very interesting. Would it be giving you the what should I say, best possible split? Over here we have one misclassification, over here we have again misclassification. How many? Here two misclassification, here one misclassification. If I talk about this, one misclassification, one misclassification. If I talk about this, no misclassification and two misclassification. Okay, and we have to consider the data points as well. So over here, if I had the misclassification, overall proportion was less because it was 2/7. Over here, it is 3/3, which is correct classification. So to me, what seems good is this definitely not. Okay, this definitely not. One of these option is going to be the correct one, which you need to just calculate the Gini index, and then you'll be able to get. Okay. I hope you're getting. You just need to calculate, the formula. If not, it's okay. Let me just write down for one of the first option, that how do you calculate it. Okay. So what we'll be having is something like this. Let me just write 7 by what we are having is 10 into 2 into 5/7 into 2/7. Okay, less we have is 3/10. Okay, just opposite of this. Then we have into 2. Then we have 0/3. How we are getting these numbers? I'll just tell you. Okay. So what is this 7/10 and 3/10 telling you? I hope you can see this. This is kind of a weighted average we are already talking about. This one. Let me just take 7/10 because we had 7 data points. So I'm just talking about this one. I'm talking about 3/10 over here. So if I just talk about this one. So we had 3 data points out of 10. 3/10 is going to be the weight. Okay. Now what is this 2 telling me? We'll come to that. Do we had any misclassification? Like what was the overall? If I talk about what should I say? Class label here and there. So out of 3, 0 wrong. Out of 3, all were correct. Okay, something like this we are having. And if I just talk about what exactly is this 2 telling me over here? Any idea? If you know the formula for the Gini index, I guess I'm also somewhere missing out. Let's just have this. I guess we missed it. We have it over here. Formula dysentery. It's same, is it? Okay. I had been using the Gini impurity. Wait, let me just check. Yeah, it's 1 minus the same thing only. Okay, so yeah, it's just the difference of post minus. Okay. So, okay. Gini index for the split is, it's the same thing, nothing difference. So what was the impurity earlier and then impurity minus? Okay, so let me just help you out over here. Yeah. So I hope you remember. So Gini index is similar to what we are having is Gini impurity only. Okay. So that means what we need to do is 1 minus p square, and whatever had been the probability for each of the class we are talking about. So for the first one, for the second one, like after the split, both what we are having, and then that will be telling me overall gain impurity what I'm having weighted by the number of data points in both the sites we are having, and what was the gain impurity initially I had. Okay, you need to subtract to find out where I would be reducing the impurity most, and that is going to give me the answer. Okay, so going by that idea, what is going to be the final answer? If you just calculate, so yeah, we already had this intuition that for this one, sorry, these were actually sounding to be fine, like either A or B. And what is going to be our final answer over here in this case is going to be this only, the first one, which is 17.6. This one. Cool. Okay, let's move on to the next one. Which of the following describes a key mechanism by which a decision tree classifies a new instance? So how does decision tree does it? So I hope you remember, very simple. What it does is it creates the hyperplane parallel to the axis. Nothing like we are maximizing the margin, nothing like kernel similarity, nothing like applying the Bayes theorem there. So it's going to be very simple. C is the correct answer. Okay, let's move on to the next one. 60, information gain. Now this is interesting. Okay, so information gain tends to be biased towards attributes with a large number of distinct values, high cardinality. The standard modification used to counter this bias and avoid selecting meaningless splits is gain ratio. Now, how does this gain ratio is calculated? So what we actually do is, for this one, we generally divide information gain by our split entropy. And that helps me in determining this overall, because this balances that thing out, the cardinality thing. Okay, and the moment we balances it, in that case it is not really that biased, which initially when we were using only information gain was. Okay, so in that case, what is going to be the final answer? I hope, like I have already told you, information gain by split entropy would be giving you the gain ratio that actually helps in balancing and removing the bias. So B is going to be your correct answer for this. We are already running short of time, but yeah, I guess you're getting what we are actually talking about over here for each of the questions. Okay, let's move on to the next one. So we talked about this, like on the continuous attributes. How does decision tree make a split? So we generally we do not really pick up a threshold, which is one of the values which we already have for the continuous variable. What we do is, for the adjacent variable or the column value we are having, we take an average over there. So for an example, if I had, let's suppose 5 and 8, I'll be looking at like 5 plus 8 by 2, some value in between. So that would be 6, not 6, yeah, 6.5. Okay, so in that case, if I had a value of 5 or something less than that, and 8 and more than that, if I want to choose a threshold in between these two, that is going to be average of these, which is 6.5, something like this. Okay, so a threshold value is found, and then we do this, like if it is less than equal to this, we'll go to the left. If greater, then we go to the right by examining midpoint of two adjacent distinct values, and so on. So, okay, cool. Continuous feature is ignored since entropy and gain index are only. So like we do not really do that. Basically, in that case, kind of a regression, the way we used to calculate the regression problems, we generally do something like that only. The mean squared error, where we are getting the less error, we generally go by that. Wherever we get lesser error for, is it for the, what kind of a problem? Oh, it's not written classification or regression, but in case of classification also, we do something like this. If it's a decision tree regression based problem, in that case, we look at where we could have been getting minimum squared error. Sorry, mean squared error is lesser. Where we have it less, that particular threshold is being chosen. Okay. Okay. Another good question. While solving a classification problem, you use a pure binary decision tree constructed by the standard greedy procedure we out. Okay. So I guess this is taken from the class. You must have not attended because it's the rank improvement course over here. So while you're training accuracy, and this is actually belonging, not like we have discussed it, and it actually belongs to one of the university question. Okay. So there also it was like this. So while your training accuracy is perfect, your validation accuracy is unexpectedly low. Which of the following in isolation, individually, that means is likely to improve? If you do this only separately, it would improve your validation accuracy. We were having what? Overfitting kind of a problem. Yes, training accuracy was perfect, but validation accuracy was less. So how do you actually improve upon that? Lift your data into quadratic feature space. If we do something like that, in that case, we are going to basically we are going for more overfitting kind of a thing. Selecting a random subset of features and use only those in your tree, not exactly. Normalize each feature to have variance 1. No. So it's like we are normalizing each of the feature. That would not really be helping me out much. Pruning the tree. How to prune? We need to decide it using the validation. Okay. So pruning would help me that how many, like how long I can go for each of the node. So what I'm saying is, so for an example, we had something splitting like this, and I'm talking about like the binary decision tree only as stated. So if something was leading to the trouble after going down from here, we would really prune it and we'll keep it until this point. Okay, that's what is pruning. So we do not really get into further things, or basically further splitting of the data points. We generally stop then and there, making that particular node as the leaf node itself used for classification. So we are going to use the pruning in that case, which actually helps in avoiding the overfitting. And how do we decide how do we prune it is already mentioned over here using the validation, cross validation. Okay, cool. Now this is interesting. Before that we have one theoretical problem, and then we'll go to the second last problem. A feature perfectly splits the data into pure nodes. The information gain in that case would be, what is going to be the information gain? If we could split the features into pure nodes. So I hope you know it's the formula already says Ig equals entropy of before splitting minus after splitting. We have weighted average of like overall after splitting. Okay, before splitting, something like this. So I don't know what had been the entropy initially, but what is going to be the entropy after splitting if it is getting splitted into the pure node? So it is going to be 0. And the moment I'm getting it least, I'm getting maximum information gain in that case. Yeah. So it's going to be maximum equals to parents entropy. Okay. I hope it's clear. Now we have the last question over here, a simple one, but still, let's see. Suppose you have a binary classification problem with a 3-dimensional feature vector. Okay, so we have x1, x2, x3, something like that. R3. You are given 50 positive, 50 negative training examples and want to build a decision tree classifier. Consider 4 possible splits at the root node for a particular, what should I say, feature we are having at the root node. Find out or find which of the below splits give the highest information gain. We need to just find out, okay, best information gain. So can you see what is happening over here? What would be the entropy over here? Just for this, what is the entropy if I just consider? So it's already 1 entropy because it's 50-50, 20 by 40, 20 by 40 every time. So it's 50-50. What about this? Entropy for this one is also 1. What about this one? Entropy for this one is also 1. Entropy for this one is also 1 because we have the same, what should I say? Positive, same number of positive and negative class. What about this one? So this one would be having what this is going to have, what should we be getting over here? Yeah, we'll be getting an entropy of 0 over here. Why? So it's 0 log 0 log 1 plus 1 log 0 kind of a thing we'll be getting. So in this case, we'll be having entropy 0. What would be the entropy over here? 5 by 50 log 5 by 50 plus 55, my bad. 50 by 55 log 50 by 55 and a minus sign over here. What about this one? Do we have a space? I need to just remove this. Let me just write down once again for this one. What we are going to have, we are going to end very soon now. Last problem, we'll be having a small guidance, or in case it's a problematic situation, it's too late, we can discuss that guidance and mentoring part in the next class, in the beginning only. So what we're going to have is minus over here 5 by 55 log 5 by 55 plus 50 by 55 log 50 by 55. What is going to be the entropy for this one? It's going to be 0 again. What about this one? Again, similar kind of a thing. 40 by 90 log 40 by 90 plus 50 by 90 log 50 by 90. This is what we are having. Now, overall, what we need to do, how many data points we have over here? 40, 40, and over here 60. So it has to be multiplied by 4 by 10. This has to be multiplied by 6 by 10. This again 8 by 80 and 20, 8 by 10. This would be multiplied by 2 by 10. Similarly, this one would be multiplied by what? 45 plus 55 is 100 only. So 45 by 100. This one would be multiplied by 55 by 100, and so on. So we know what we need to do. It's like the simple thing we are having right now. Okay. So you just need to calculate what are the splitting we are getting over here, because one thing is for sure over here. We had some entropy at this point, which is going to be constant for all of these. For all of these four, we are going to have that constant. Now, what is only the changing part is in information gain, the weighted average entropy. So, 4 by 10 into 1 plus 1 into 6 by 10 will get for this one. What is the value we are getting over here? What is the value of weighted average entropy over here, here? Whichever is minimum, that is going to be the best split. I hope you are getting that. So that would be giving me the best possible split for me. What shall be used over here? So what do you think is going to happen? What is going to be the one which will be giving you the best split? So this seems to be like a very low, and something from this would also be coming up. And I'm already having, this is also kind of very close to the perfect example. Can you see? 50 were the majority class and only 5 were like from the other class. Over here we have nearly like equal, like it would be more. This is something seems to be better because this was already 0, perfect. Over here it's like 5 out of 55 had what should I say, would belong to the other class, and 50 out of 55 would be belonging to the perfect class. So in that case, you can see what is happening over here. This is kind of already going by the best possible case. This was already best, purest form node. So C is going to be a best split without even calculating. I have told you how to calculate, but if you don't want, you can see by analyzing only, you can most of the time answer each of these questions very easily. Okay. So that was our last problem which we wanted to solve. And for the guidance part, I already had something in my mind that how to attempt the test series. But I guess we have already past our proper time which we have decided, which 1.5 hours. So let's not discuss this right now. We can discuss it in the next session within the starting only. Okay. So I hope you could enjoy this problem solving session where we had like 20 questions being solved from overall KNN plus naive Bayes plus your decision trees. I hope you really enjoyed this session. You loved this session. Make sure to share it with your friends. Don't forget to like this session if you're enjoying, if you're getting something out of it, if this is helping you out in your preparation. Okay. So thank you guys. See you guys tomorrow. Till then, bye bye. Take care. Thank you guys for watching this session live.